Hello students, in this video we'll discuss matrices as linear maps from one Euclidean space to another Euclidean space. So let's suppose that A is an m by n matrix of real numbers. Okay, and let's be given an n-dimensional column vector x, and x x1, xn, an n-dimensional column vector. Okay, so since A is an m by n matrix, let's write it out. So here's what A looks like. So A has this form. So A has the form A11 down to A1n, all down to A m1 through a mn. That's what our matrix looks like. And what I'm going to do now is I'm going to define, so let's define A1. And what will A1 be? A1 is going to be this first column vector, A11 down to A m1. I'll define A2 to be that's going to be my second column. So it's going to be A what? That's going to be A12. First row, second column, A22, AM2. And finally, I'm going to find AN to be the nth column. So in other words, A1 is the first column, A2 is the second column, A3 is the third column of the matrix A, and AN is the nth column of A. So that's going to be an A1N down to AMN, okay? Now note that A1, A2, A3, AN, all of these vectors are what? They live in m-dimensional space. So this is an m-dimensional thing. This is an m rows by one column, so that's an m by 1. This is an m by 1. This is an m by 1. This thing, of course, this x over here is what? Is an n by 1, so that's an n by 1 thing. Those things are m by 1. And now what I'll do is this. I'm going to define ax. So our definition of ax is the following. So ax, define ax, this product of a and x, to be what? To be x1, a1 plus xn, an. This is a linear combination of the columns of A. That linear combination of the columns of A is exactly equal to an m-dimensional vector. So this ax is an m-dimensional vector. Okay? And so now notice two things. We have two important properties. So here's a very simple proposition to prove. So the proposition that's very simple to prove is the following. So proposition is that A applied to vector x plus vector y. Well, let's think what vector x plus vector y will be. That's going to be what? If I had x plus y, if y was this vector over here, so if y was the vector y1 down through yn, then of course x plus y would be x1 plus y1. So I'd have what over here? I have an x1 plus y1. So that would distribute to the a1 with an x1, a1, and a y1, a1. So this is exactly equal to ax plus ay. And the second is that a of lambda x will be lambda a of x. So the proof of this proposition just follows from a direct calculation. So the proof is just direct calculation. It's a direct calculation of this thing of star. We can sort of think of that if I replace x with lambda x, it's going to be a lambda here, a lambda here, a lambda here, a lambda here. I can pull that lambda out of the entire sum. Okay? If I have an x plus y, what will happen? All x1 plus y1, I can break that up into x1 times a1 and y1 times a1. The same with all of them, so I can basically commute all those things and relate them. I get these two properties. So this proves that A is a linear operator, right? So A is a linear. This implies that we have a linear operator. Okay? So A is a linear operator. In particular, what that tells me is that A as a matrix, this n by n matrix, is really a mapping. I can input something in n-dimensional Euclidean space, and I'm going to output something in m-dimensional Euclidean space. That's going to be an m over there, so m-dimensional Euclidean space. And this is beautiful. So this is a linear operator. This is a linear operator. Okay? So of course, it's very difficult to visualize what's happening between high-dimensional Euclidean space and high-dimensional Euclidean space, but we want to always come back to some simple examples we know about in just standard Euclidean space. Let me give an example of this. So here's let me give a sort of an abstract example first and then a particular example. So the abstract example is I have this matrix over here, 1, 2, 3, 4, 1, 1, negative 1, 2. So this is a what? This is a 4-row by 2-column matrix over here. If I was to plug in, if I was to operate on a what? You operate on a two-dimensional vector. So my two-dimensional vector over here is going to be, I'll say A, B sort of abstractly. What this will be is this is going to be A times the first column of the matrix, 1, 2, 3, 4, plus B times the second column of the matrix, 1, 1, negative 1, 2, right? And so we see over here that I plugged in something that resided in two-dimensional space, and this thing over here is clearly a four-dimensional vector, right? So it's a 4D vector. And I plugged in a what? I plugged in an arbitrary 2D vector. That was a 2D thing. So in other words, this 4x2 matrix is taking a two-dimensional space into a four-dimensional space from R2 to R4, okay? Now, of course, some of the ones we see from classical geometry. So for example, if I did this, if I said, let me look at this matrix over here. Let's do the matrix, let's do something different than 0 first. So if I did, let's do this. If I did the matrix 1, 0, 0, negative 1, and I applied this to a two-dimensional vector. Remember, this is a 2x2 matrix, so I'm going to map two-dimensional space into two-dimensional space in a linear way. This will be what? This is going to be x and then negative y. You might say, well, that's a big deal. That's a very simple calculation to do. That's really just x times 1, 0. In other words, you don't affect the x entry at all. And how do you affect the y entry? The y entry is affected by hitting it with a negative 1. And of course, what does this represent geometrically? Geometrically, what this would say is if I take a point in R2, so here's my x and here's my y, if I give you a vector xy, there's my vector xy geometrically, what this operation is going to do, this operation from this matrix, is going to take xy, and if I hit it with this matrix over here, 1, 0, 0, negative 1, the output is going to be the reflection. So in other words, this matrix corresponds to reflection over the x-axis. Reflection over x-axis. So in further videos, we'll study more general reflections, more general rotations, and different sort of classical operations from Euclidean geometry that can be put into a matrix form, and we'll understand them from the perspective of a transformation in a matrix. Thank you very much.